In the previous video, we saw that the number of minority carriers injected across the PN junction increases exponentially with a forward bias voltage. Now we look at the IV characteristics of the PN junction diode. This is the diode equation. The diode current I equals the reverse saturation current I naught times e to the QV over KT minus 1. The reverse saturation current I naught depends on the doping levels and the physical size of the diode. At room temperature, the E exponent, QV over KT, is V over 0.026 volts. When V equals 0, e to the 0 is 1, 1 minus 1 is 0, and the current is 0 as expected. When V is more than about 0.1 volt, the exponent term is a large number and the minus 1 can be ignored. Then the current is just an exponential function of V. When V is more negative than about minus 0.1 volt, the exponent term is close to 0 and can be ignored. Then the current is just minus I naught, the reverse saturation current. Here is a graph of the diode current as a function of voltage, the IV plot. The current increases by a factor of 10 for each additional 0.06 volts applied, for example here, or anywhere else nearby. Enlarging the portion of the graph near 0, you can see the current is 0 when the voltage is 0, or minus I naught at negative voltages. The diode is said to operate like a one-way valve. To see why, let's look at the IV plots of the related components. For a resistor, the IV plot is a straight line with a slope equal to 1 over the resistance. For an open circuit or infinite resistance, the plot is a horizontal line on the x-axis. The current is 0 no matter what voltage is applied. For a short circuit or zero resistance, the plot is a vertical line on the y-axis. The voltage is 0 no matter how much current is flowing. A perfect valve would operate like an open circuit when the voltage is negative, or a short circuit when the voltage tries to go positive. The current can flow only in the positive direction, and it does so with zero resistance. A diode is similar to a perfect valve. With a negative voltage applied, the current is very near 0. With a positive voltage applied, a large current flows with very little resistance after a small voltage threshold is reached. A PN junction can operate as a solar cell. Light shining on the semiconductor provides energy to create new electron-hole pairs. Minority carriers at the junction are swept to the opposite side, where they become majority carriers and escape from recombination. The newly created particles move away from the junction, providing a current to drive an external load. A light-emitting diode is a solar cell operating in reverse. An external power source feeds a steady supply of electron and hole majority carriers toward the junction. They are injected across the junction, where they become minority carriers and recombine with the majority carriers there, releasing energy as light.